Good day everyone, and welcome to our presentation. Today, we delve into the fascinating intersection of language modeling and motion forecasting with our paper, MotionLM, Multi-Agent Motion Forecasting as Language Modeling. Imagine road users as participants in a dialogue, their actions and reactions forming a complex conversation. Our research introduces MotionLM, a model that deciphers this dialogue, predicting road agent behavior with unprecedented accuracy. Stay tuned as we unravel this groundbreaking approach. Our primary motivation is to enhance the prediction of road agent behavior, much like participants in a dialogue, anticipating their maneuvers and responses. We aim to apply an approach akin to how language models capture the distribution of conversations. However, existing models have limitations. They often decompose the joint distribution into independent per-agent marginal distributions, capturing correlations but failing to infer causality. To address these issues, we introduce MotionLM. This model uniquely combines trajectory generation and interaction modeling in a single process. It's trained to maximize the log probability of token sequences among interacting agents, providing a more comprehensive and accurate prediction of road agent behavior. This innovative approach allows us to better anticipate and respond to the dynamic nature of driving scenarios. Imagine road users as participants in a dialogue, continuously exchanging actions and reactions. This dynamic interaction mirrors the fluidity of communication. However, predicting these interactions is a complex task. Traditional models often simplify this by breaking down the joint distribution of agent behavior into independent per-agent marginal distributions. But this approach has its limitations. It fails to capture the future dependencies between the actions of different agents, leading to inconsistent scene-level forecasting. Now, take a look at the figure on your right. This is an overview of our proposed solution, the MotionLM model. It's a novel approach that combines trajectory generation and interaction modeling in a single, temporally causal decoding process over discrete motion tokens. This model is trained to directly maximize the log probability of these token sequences among interacting agents. It's a significant step forward in the field of multi-agent motion forecasting. Our motivation stems from the need to anticipate the maneuvers and responses of road users, much like how language models capture the distribution of conversations. However, existing models present a problem. They decompose the joint distribution of agent behavior into independent per-agent marginal distributions. This approach is insufficient for planning systems as it fails to represent future dependencies between the actions of different agents. Furthermore, existing joint prediction approaches have their own limitations. They separate the process of marginal trajectory generation and interactive scoring. These models do not explicitly model temporal dependencies within trajectories, which can lead to less realistic reaction predictions. This is a significant drawback as it limits the ability to accurately forecast the behavior of road agents. In the next part of our presentation, we will introduce our proposed solution to these challenges. In the realm of modern sequence models, a key challenge lies in accurately predicting the behavior of road agents. Existing models can capture correlations, but often struggle to infer causality between agents. This is a significant issue, as understanding the likely maneuvers and responses of road agents is crucial for safe and efficient navigation and planning. Despite substantial progress, current models that provide marginal predictions have been found to be insufficient for planning systems. They often fail to represent the future dependencies between the actions of different agents, leading to inconsistent scene-level forecasting. To address these issues, we introduce a novel approach, MotionLM. This model combines trajectory generation and interaction modeling in a single, temporally causal decoding process. It's trained to directly maximize the log probability of token sequences among interacting agents, producing joint trajectories step by step. This approach offers a promising solution to the limitations of existing models, and we look forward to sharing more about its design and performance. Our research introduces a novel model, MotionLM, which is designed for trajectory generation and interaction modeling. This model is trained to maximize the log probability of token sequences among interacting agents. At inference time, it produces joint trajectories step by step, providing a dynamic and interactive representation of agent behavior. Diving deeper into the technical details of MotionLM, it consists of two main components, an encoder and a trajectory decoder. The encoder processes initial scene elements, while the trajectory decoder generates future agent motions. The model performs cross-attention to scene encodings and self-attention along agent motion tokens, allowing it to capture complex interactions and dependencies. One of the unique aspects of MotionLM is that it is entirely latent, variable, and anchor-free. This means that the multimodality, or the variety of possible outcomes, emerges naturally from the sampling process, rather than being manually enforced. This approach allows for a more flexible and realistic representation of agent behavior in various driving scenarios. Our research introduces a novel model, MotionLM, which is trained to match the observed behavior of multiple agents. This is achieved through a maximum likelihood objective over multi-agent action sequences. To ensure stability and avoid sampling during training, we employ a technique known as teacher forcing, where previous ground truth tokens are provided at each time step. Now, let's delve into the factorization aspect of MotionLM. The model factorizes the distribution over joint future action sequences as a product of conditionals. This means that we treat agent actions as conditionally independent at a given time, based on previous actions and the scene context. Importantly, our model is entirely free of latent variables. The multimodal predictions it generates stem purely from categorical token sampling at each rollout time step. This unique approach allows us to capture the complex dynamics of multi-agent interactions in a more realistic and efficient manner. Our research introduces a novel approach to multi-agent motion forecasting, which we call MotionLM. This model is designed to preserve temporal dependencies, meaning that the inference process follows a directed acyclic graph. This is a crucial aspect of our model, as it allows us to make conditional forecasts that closely resemble causal interventions. By adhering to this structure, we can eliminate certain spurious correlations that might otherwise occur if we were to disregard temporal causality. This is a significant advancement in the field, as it allows for more accurate and realistic predictions of agent reactions, which is a key factor in planning. In essence, MotionLM is a generative framework that is capable of capturing the substantial multimodality in driving scenarios, while also preserving the temporal dependencies that are so crucial to accurate forecasting. Let's delve into the architecture of our model, MotionLM. This model is designed to encode heterogeneous scene features relative to each agent in the scene. These features are then transformed into scene embeddings. The trajectory decoder then rolls out discrete motion tokens for multiple agents in a temporally causal manner. This process is akin to a conversation where each agent's actions are influenced by the others. The final step involves recovering representative modes of the rollouts using a simple aggregation method, such as k-means clustering. This architecture allows us to generate multimodal joint trajectories by directly sampling from a learned distribution of discrete motion token sequences. This approach is unique as it does not rely on latent variables or beam search, common in most autoregressive trajectory predictors. As we look at the figure on the right, we can see the joint prediction performance of our proposed model, MotionLM, across varying interactive attention frequencies and numbers of rollouts per replica on the WOMD interactive validation set. The vertical axes display joint metrics for an 8-replica ensemble. This clearly illustrates the effectiveness of MotionLM in achieving state-of-the-art performance, with a notable 6% improvement in the ranking joint MAP metric. Now, let's delve into the core of our novel approach to interactive motion forecasting. We've essentially reimagined it as a language modeling task. This innovative perspective allowed us to introduce a temporally causal decoder over discrete motion tokens. This decoder is a key component of our model, enabling it to capture the complex dynamics of multi-agent interactions in driving scenarios. Our proposed model, MotionLM, brings together trajectory generation and interaction modeling in a unique, temporally causal decoding process. It's trained to maximize the log probability of token sequences among interacting agents. What sets it apart is that it's entirely latent, variable, and anchor-free, with multimodality naturally emerging as a characteristic of sampling. Now, let's talk about the significance of the model's temporally causal conditional predictions. This is a feature that is largely unsupported by current joint forecasting models, marking a novel approach to the problem. It's this innovative aspect that allows MotionLM to capture the dynamic and complex interactions of road agents, paving the way for more accurate and realistic predictions in driving scenarios. Looking ahead, we have exciting plans for the future. We aim to utilize our trained model within model-based planning frameworks. This would allow us to form a search tree over the multi-agent action rollouts, enhancing our ability to predict and plan for complex driving scenarios. Additionally, we are keen to explore distillation strategies. By learning from large, autoregressive teachers, we can develop faster student models. These models could be deployed in latency-critical settings, providing real-time insights and predictions. This combination of leveraging our model and exploring distillation strategies promises to push the boundaries of interactive motion forecasting.